Terbium-160 looks like this. 160, 65 TB. Decays via beta minus decay with a half-life of 73 days. In a given sample, there are 4 by 10 to the 18 atoms of terbium-160. Write an equation for this decay and determine the number of terbium-160 nuclei remaining after 1 year, 365 days. You might notice, and if you've done your homework, you'll notice that these numbers often fit very nicely into this number, okay? And in this case, it does. Have a go at this answer, please, people. Okay, here we go. Here's the key, beta minus decay. I'm going to put an X for our daughter nucleus here. We're going to say that this is beta minus, so I can say charge of -1. I'm going to call it an electron, mass number of 0. What number goes here if this is -1? 66, thank you. And this, of course, the mass number doesn't change. What else do we get? Antineutrino with beta associated with beta minus, and a gamma ray photon. Good. No, it doesn't. You might notice, people, that your book actually sometimes in the, they can do this. They put the zeros on that side, or they put the 160, 66 like that. That's also legal. I try to stick to one side. Legal when it comes to answering the question in the exam. Will you lose marks for it? No, you will not. As long as it's clear. Also, you might have noticed that they sometimes put little 0 charge, 0 mass there for the gamma ray photon. That's good too. You can do that. Don't need to. 365, 1 year, 73, half-life equals 5. 5 half-lives pass. 5 half-lives pass. What do I use to calculate the number of nuclei remaining? N. Yes, Paul. Yes. Yes. That's right, where little n equals the half-life, n naught is the original number of nuclei remaining. So we get 4.0 by 10 to the power of 18 over 2 to the 5, number of half-lives. And we get an answer of 1.25 by 10 to the 17. Nuclei remaining. I can't. Oh, remaining. 17. BQ if it's activity. Same thing. It's fine. That's fine. Okay. One more question from our text. This one you need to draw a graph. Once again, I'll give you a couple of minutes to have a go at it yourself, and then I'll finish it. I'll have a go at it. Magnesium 23, and that looks like, yeah, 2312 Mg magnesium. Decays via beta plus decay with a half-life of 12 seconds. Given sample of magnesium contains 200 grams of magnesium-23. Plot a graph, write an equation. Have a go at this, please. I'm going to say here, so this is our mass on the y-axis in grams. This is our time in seconds. We start with 200 grams, 150, 100, 50, 12 seconds, 24, 36, 48, did I get enough here? 60, yes, 72. First 5 half-lives. 72 seconds. Okay, that's good. So let's plot it. It's easy enough to plot. Most people can do this. We're going to see an exponential curve. I've kind of made this a little bit small. After 1 half-life, we've only got half of the sample remaining. Up to 2 half-lives, we've got half of that, or a quarter. 3 half-lives, half of that again, an eighth. 4 half-lives, half of that again. 5 half-lives, half of that again. 6 half-lives, half of that again. Kind of like that. I have trouble drawing these curves. Always start well. I'll leave that like that. Yeah, I don't know whether this program has an exponential curve function. That'll do. Hopefully you can do something better than that. Should be exponential. What about the... okay, so one thing I will do is I'll go back and check to make sure I've answered that question, because I've spent a bit of time on this, getting carried away with the things that I know. Now I'll just go back and say, plot a graph of the amount of magnesium-23 remaining against time for the first 72 seconds. I have answered that question. 2. Write an equation for this decay. Yes, so we've got beta plus decay. So I'm going to go straight to the beta plus particle. Beta, yeah, we can use a beta. +1, 0 mass. What do I need here? Yes. Yes. 11, that's right. Which happens to be sodium. Yes, excellent. Full marks. Good. Any questions there? This device, essentially this is a table for the patient to lie on. The patient can move through this device here, which is just a big detector. Shush. Thank you. This is just a bunch of detectors, in fact, in a circle. Okay, so detectors in all directions here. What does it use? Well, see, living tissue contains lots of elements: oxygen, hydrogen, carbon. What else did I say? Fluorine and nitrogen. Fluorine and nitrogen. Now, and it depends on the place in the body that you're looking at. I mean, of course, there's different concentrations of this stuff. Hydrogen and carbon are pretty, they're throughout the body, they're everywhere. But fluorine and oxygen and nitrogen, not so much. They tend to be associated with metabolism in the body. Chemical processes in the body, and we can commonly known as metabolism, will cause concentrations of certain elements. So that's useful in this application. Fluorine 18. This is an isotope, a radioactive isotope. Of fluorine, of course. It's a radioactive isotope, or a radioisotope of fluorine, which of course emits radiation. This type of radiation, beta plus. This is useful. The body uses fluorine in glucose metabolism. So, how do you think this is useful? When they ask, when a patient comes in to say they know that they've got a cancerous tumor somewhere in their body, they give them some of this fluorine 18. I think it's in a water. It contains some of this stuff. They ingest it essentially, and they ask them to lay very still for quite a time, for maybe an hour or so. Why would they do that? Yes, it's got to be ingested into the body. So it's not enough just to swallow the stuff. It sits in your stomach. That takes 7 seconds or thereabouts to get to your stomach in the first place. Then your stomach swishes it around, and it can take up to a couple of hours before the stomach allows it to go on into the intestine, which is where it's taken up by the blood system. Okay, so, and then the blood system has to send it to certain places in the body. So, but they ask you to sit very still. Considering fluorine is used in glucose metabolism, why would they ask you to sit very still or lay very still? Yes, certainly partly because the body's going to be looking to use that as energy, isn't it? Partly true. Not so much so it's stored. It's going into glucose metabolism. If you think, if I swallowed this stuff and then I went for a run, where's the glucose metabolism going to be happening? Everywhere in your body almost. Yeah, that's right. Instead of being focused at a place where metabolism is occurring even when you're laying still. Cancers are growing. Cancer cells are multiplying and growing constantly. It doesn't matter whether you're exercising or not. I don't know the effect actually of exercise on cancer cell growth, but if you go and exercise after this, your muscles are going to be asking for that glucose, and the blood is going to be delivering that glucose, or that metabolizing glucose in your muscles, and you don't want that to happen. You want it to focus in areas where the cancer is. So they ask you to lay very still. Why I'm swallowing this isotope of fluorine. Why is it that this isotope of fluorine is used exactly the same as regular fluorine in the body? Yes. Exactly. So the body processes work via chemical reactions. This means the body, or the body will not discern between isotopes of any substance. The body just sees the chemistry only. So here's my patient, and this person ingests some of this fluorine 18, and that fluorine 18 concentrates in certain areas in the body. It goes elsewhere in normal metabolism all over the body, but it tends to concentrate in certain areas. And we're particularly interested with regard to cancer, because we can use that now, because we know that this fluorine 18, once it's in there, it's going to throw off stuff indicating where it is in the body. If we have a machine that can measure where that stuff is, or how far this emanation has come from, then we will be able to see this cancer, or this group of cells rather. By ingesting fluorine 18, I'll just say body processes will send to areas of high glucose metabolism. Okay, so we know this fluorine 18 decays via beta plus decay, which is just a positron, isn't it? What do we know about positrons and them moving through any matter? Yeah, they're gonna, once they slow down enough, they need to slow down, lose some energy, so interact with some matter, and then slow down. they're going to very quickly come into contact with this guy. An electron, which is the positron's, yes, that's right, positron's antiparticle. What happens? Annihilate each other. Yeah, that's right. I might get a new page. The positron and the electron annihilate each other. Now, if I stop there, what's wrong with that? Why do they need to emit 2 gamma ray photons? Conservation of energy, conservation of momentum. Yeah, that's right. Absolutely. You can't just have these two things disappear and nothing happen. They had mass, low mass, but they had mass. They had energy because they were moving. They can't just disappear into nothing, into thin air. So here comes our positron, and here comes our electron, and there's not an explosion. They annihilate each other, and this stuff comes off. I know, I know. I don't know where I've been drawing this picture for a while, and I always draw an explosion-looking thing, but it's not an explosion. Not an explosion. They annihilate each other. Not. They don't. Yeah. And you guys watch too many movies. Annihilate means to make not there anymore. They don't exist anymore. Yeah, no, they reach over their back, pull a weapon, and blow each other away. No, that's not what happens. They come into contact and disappear. They disappear. How can mass go away? Well, it can turn into energy in the form of. No, it's not. Absolutely, you're right. They can turn into something else. Turn into something else. 2 gamma ray photons. So what we see is the electron and the positron and the electron coming in, they don't exist anymore. But in their place, we see 2 gamma ray photons move off in opposite directions. Mass turns into energy. That's right. Turn into 2 gamma ray photons. No, not necessarily. No. Well, that's the only one I want you to know at the moment. All right, yeah. They turn into gamma photons. Now, let's have a look at how we would do this. The mass of an electron or a positron is equal to 9.11 by 10 to minus 31 kilograms. And we've got 2 of them. 2 times 9.11, 10 to the minus 31 kilograms, is equal to yes, very good. Good to see your. Some people are starting to do the calculations in their head. It will help you confirm that your answer is correct as you move through. If you're able to do that, see how you go. See if you can guess approximately how much this one's going to end up as. So this of course is our delta M mass defect. Energy is equal to mass defect times c squared. No, no. Yeah, so they've got their own kinetic energy, don't they? And we're only looking at their mass in this case. That's beyond the scope of this course. A little bit too complicated. By 10 to the power of minus 30 times by c squared, whoop, 16, 9 times 10 to the 16. Yeah, nice. That's good, I think. Yep. And that's it. That's in joules, of course. We calculate energy in joules. We need to change it EV. 1.022 by 10 to the 6 EV. And the book changes it to 1,022 KeV. 2 photons at 511 KeV each. Not unless you're asked to. Often you are asked to, though. Okay. Okay. So we have now, let's draw our patient again laying down. And we have gamma ray photons. All right, please. Gamma ray photons being emitted all over the place in opposite directions. Now, if I have a device that can measure when corresponding photons are emitted or where they are emitted from, and that's where this device comes in. So we can place our patient inside this array of detectors inside here, and what happens is essentially. Oh, actually, I have another picture from the text, which is quite good, which I didn't use last time. Here. So gamma ray photons. Imagine that there's something of interest that metabolizes glucose in the person's head. It might be a cancer. As the emissions happen, for each emission this way, there's an emission in exactly the opposite direction. This detector here can detect those, and what they can do is by the difference in time it takes for this emission and this emission to reach the detector, they can pinpoint where the original atom was, that nucleus was, the nucleus of fluorine 18. And what happens is, over time, as this detector picks up emissions, it pinpoints them, and we build a picture of exactly the right shape of the tumor. Okay, over time. So I better write some of that stuff there. After quiet, please, people. After travelling about 1 millimetre, this positron will slow enough to interact with an electron. And so the beauty of this is it's not so far. So we know that these emissions are coming from within 1 millimetre of the original nucleus. Gamma photons are emitted in opposite directions the detector or detectors will measure the time difference and pinpoint the origin. With many emissions, a picture of the tissue of interest is formed. Fluorine 18 has a half-life 110 minutes. Fluorine 18, as you know, is useful for glucose metabolism. Oxygen 18, T-half, 2.1 minutes. This stuff has a really short half-life compared to the fluorine anyway. This can be used to measure blood flow. What do we need? Now, this device here is very expensive. What do we need very close to that device? Cyclotron, that's right. In order to make this stuff, we need to be able to bombard some element with neutrons. Neutrons are no good because what you can't accelerate them, can you? So we bombard them with protons, whatever it may be, with a cyclotron, and we can make a whole lot of this stuff, but it only has a half-life of 2 minutes. So the patient needs to be close by, and so does the positron emission tomographer. Okay, so if you buy if you're a hospital and you're looking at purchasing one of these things, which costs in the millions of dollars, you also need to purchase a cyclotron, which costs in the millions of dollars also. And as a result, there's not many. I think only a few years ago, maybe 2 or 3 years ago, there were only 12 in Australia. And undergo what? Oh, yeah, so you give it a positron, you change that nucleus. Yeah, it's going to tend to have an extra proton. So going to beta plus decay. Yep. Yep. Just the last bit here, please. This here's a typical decay that we might see by beta plus decay. I said oxygen 15. This is oxygen 15, not oxygen 18, sorry. Oxygen 15 decays by beta plus decay to nitrogen beta plus gamma ray photon plus neutrino and fluorine 18. See if I can fit it in here. 18 fluorine is 9, isn't it? Yeah, 9. Atomic number 9 decays via beta plus decay as well to oxygen 18. Whoops. It's a bit hard to read. I'm squashing it in here. Oxygen 18. Beta plus particle. Positron. Gamma ray photon. Neutrino. Oxygen 18 is oxygen 18, no, it's probably not stable either. It's so that's going to decay also. That's right. Yeah, it's a good question. So this is going to decay to oxygen 18. Oxygen 18 is going to decay over some time. I don't know what the half-life is or anything like that. And how it decays, it might not be by beta plus decay. It might be by beta minus decay. And so you're not going to see, a PET scanner is not going to pick up the emissions that this causes necessarily. Okay. That